In this lecture, we are going to look at the PCH 321 past question, but this time it is the practical question. And in this practical session, we are going to look at the partitioning or distribution coefficient. Now, when we talk about partitioning is a separation technique generally. It's a method of extraction of a particular substance based on solubility in two different immiscible liquids or two different immiscible solvents. Is that okay? So that's what partitioning is all about. When we talk about, let's say you have substance A, and you have two solids, two solvents, B and C. Now, if substance A is soluble in B and at some point it is also soluble in C to a very, or let's say substance A is soluble in B to a high degree, but it's also soluble in C a little, but not to a high degree. But B and C are immiscible. B and C are immiscible. Is that okay? And let's say substance A is in C initially, but they are insoluble. So what do you normally do? You can add substance B to it. Now, when you add substance B to C, it means all the particles of A in C will be soluble in B. Is that okay? Let me come again. We have two substances, two solutions, or two solvents rather, B and C. And let's say A is in C normally, but both of them are insoluble. Now, however, substance A is soluble in B. It's soluble here, but insoluble here. Now, for you to remove substance A from C, what do? You add some amount of B into C, so that the B that you added into C will actually react with the A. Recall that B and C are immiscible. So if substance A actually reacts with B, that means it's insoluble in B, and B and C are insoluble. It means you cannot separate the two layers in such a way that you are now having a large concentration of A inside of B and a very low concentration of A inside of what? C. Is that okay? So that is the general idea of partitioning. It's a separation technique. Now, in the practicals, especially, you will be given a salt. Now, in chemistry, when they say salt, they don't mean sodium chloride only, or most time they don't mean just any kind of salt. When you talk about a salt, it means a solid substance, a pellet, anything that you can actually touch that is solid, like those white crystalline pellets. That's what they call salt. So it may even be a base, but in chemistry, it is called a salt. Are you getting it? It may be any other thing, but in chemistry, it is called what? A salt. So long as it is solid crystalline form, it is called a salt. Is that okay? Now, the procedures will be given to you. Firstly, if it's for you to put your salt inside the separating funnel, because what is used is the separating funnel to separate the two immiscible layers. Now, when you put your salt in the separating funnel, let's say you add water to the separating funnel, or you add the oil first. Let's assume you add oil first, or anything, one of the solvent, and then you shake. After shaking, you add water, and then you shake. Then you allow it to settle down. After allowing it to settle down, what will happen is you have two different layers. Now, what I mean is, for the first thing, you are going to add the salt. Like I told you, when you talk about salt, it's crystalline solid. Then after the salt, the next thing is you add maybe your organic phase or organic solvent. Now, after that, you shake. Then you are now going to add the last thing, which is water, and then you shake again. After shaking, you're now going to have two layers. One of the layer contains the organic phase, and the other layer contains the what? Contains the liquid phase, which is aqueous phase or water phase. Now, both of these two layers, one will be on top while the other one will be under based on the density. The more denser one will be under while the less denser one will be on top. So in most cases, the water is usually more denser than most of all these organic solvents. However, there are some of all these organic solvents that are denser than water. So if a situation where water and some oil or organic solvents are given to you, the organic solvent may be the one on top, while water will be the one under, based on the one that is denser. So now that you have two layers, what you are going to do is to clamp it here on your rator stand, and then you separate them. All right, you loose them and then allow the phases to separate. Let's say this is the first phase here, which is the water phase. You allow it to separate. Then after allowing it to separate, you keep it at the corner somewhere here. I don't know why these children they cry like rat children. You have something like this distracting me. All right, so this is the liquid phase, and then also from here you now pipette 10 ml into another conical flask. That means from here, the amount you got here, you prepare 10 ml here, and either 10 ml, you carry it here. This is supposed to be a conical flask, and titrate it with a known amount of sodium hydroxide. You titrate it with a known amount of sodium hydroxide. Now, note something, that in chemistry, what you are doing in titration is standardization. Standardization means you know a particular something, the concentration of what is here, which we call a primary standard. Now, if you know the exact concentration of this, what you are going to do is to use this exact concentration to estimate the concentration of what is here, of the salt that will be in the aqueous phase. Are you getting in that? So if this one is the aqueous phase, what we are saying is that when you titrate, titration is like standardization. I told you standardization is trying to know the actual concentration present. Is that okay? Trying to know the actual concentration present. So when you take this one now, which is your aqueous phase, you titrate it. This titration will tell you the exact amount of the salt that you put here that will be present in the aqueous phase. The exact concentration that will be present in the aqueous phase. Is that fine? So that is the process of the practical. Now, having done that, you also remove the let's say organic phase, and then you titrate. That will tell you the actual concentration in the organic phase. Is that fine? Now, there is a trick that you need to be very careful of here. If the salt that they gave to you is an organic salt, let's say it's an organic compound, there is very high tendency that your titer value, listen, if it's a very high this thing, there's a very the salt that is given to you, if it is an organic compound, there's a very high tendency that the titration value or the titer value for the organic phase will always be higher than the titer value for the aqueous phase. Why? Because organic compounds are more soluble in organic liquid or organic solvent than in aqueous solvent. So it means that there will be a higher amount of that substance in the organic phase as compared to the aqueous phase. And the higher the amount of the substance, the higher the amount of sodium hydroxide that will be required for the titration. The higher the amount in the organic phase, the higher the amount of sodium hydroxide that will be required for the titration. Why? Because it's more like 1 mole of this. 1 mole of this, let me just put a relationship here, is reacting with 1 mole of this. So if the number of moles here is very high, it means you will need more of the volume here, or more moles of this to react with this. And the moles here is represented by the titer value. Are you getting it now? So in most cases, your titer value for the organic phase will always be higher than the titer value for the aqueous phase, especially when the compound in question you are trying to separate or partition is in both an organic compound rather. Is that okay? Now, in this practical, we use phenolphthalein as indicator. Now, the reason why I use phenolphthalein as indicator is because the salt they actually gave, the one we did was benzoic acid. And benzoic acid is what? An acid. Phenolphthalein is colorless in an acid, but changes to pink in basic solution. So it means, look at the general idea now. Phenolphthalein is colorless in acid, but changes to pink in basic what? Solution. So when you are titrating here, the base is neutralizing the acid. Now, a time will come where there will be no more acid present here for the base to neutralize. So the base will actually surface. And we say phenolphthalein is what color in a base? Is pink. So instead of it to be having that colorless, now you are now having the pink, which indicates that all the acid here have been reacted with. Is that okay? The reason why the color changes from colorless to pink is because, like I told you, phenolphthalein is colorless in acid. But when you are titrating with a base, now phenolphthalein is somehow pinkish in base. So at the initial start of the titration, you have more of the acid here, so it becomes still colorless. But a time will come where all the sodium hydroxide has reacted with the acid that is present here, so there will be no more acid here. Hence, the color will now show somehow pink to tell you that no more acid here. What we are now having here is a base. Are you getting it? Because you have neutralized all the acids, so the base will actually surface. Any base you add more will surface. Now will not tell you phenolphthalein is pink in what? In basic solution. So that is how the indicators they work. Is that okay? Now, having learned this, what we are now going to do now is to come to the instruction for this practical. Now let us go to the practical session, and then we'll see the instruction that was given to us. Say a salt was partitioned between organic and aqueous phase, and separating funnel was used to separate the two layers. Now, pipette, it means in this practical, if they really want us to work on this practical, it means they will do the partitioning for us. Are you getting it now? The partitioning will be done for us. So all what we need is that they will label this organic and this what? Aqueous phase. Is that okay? Say now pipette 10 ml of the organic layer into a 250 ml conical flask, and then add 3 drops of phenolphthalein as indicator and titrate with 0.2 mol sodium hydroxide. Note the titer value. Then also pipette 10 ml each of the aqueous layer and titrate with 0.2 molar sodium hydroxide using phenolphthalein as indicator. Hence, calculate the amount of salt in the aqueous layer and organic layer. What is partition coefficient? What is the partition coefficient? And then state the precautionary measure used in the experiment, and then write the structural formula of benzoic acid. Now, if you are asked to do practicals like this, it becomes very, very easy somehow. Now, the reaction or this salt that was given is actually benzoic acid. Are you getting it now? It's benzoic acid. And benzoic acid is something like this. We have right? So the first thing before you can calculate is to write your equation of reaction plus sodium hydroxide. Now when benzoic acid react with sodium hydroxide, it's going to form sodium benzoate and water. Right? It's more like acid-base reaction. It's going to form sodium benzoate plus water. So you can come here and label benzoic acid. That is the salt that was given for that practical. Sodium hydroxide is this. Now, although the salt was not mentioned, but from the general thing, I believe they are going to tell them later, but I think the salt is sodium benzoic acid, since they say draw the structure of benzoic acid. And also that was what was given in the the practical. Now we have benzoic acid, sodium hydroxide, and then you have this, which is what is it called? sodium benzoate, and then water, H2O. Now, for this practical, sometime if this thing was not mentioned, but you should also know, because definitely you need the equation of reaction to calculate the partition coefficient and the amount. All right, so this one now, the molecular formula for benzoic acid is 6,7H6O2. Then of course plus sodium hydroxide to give us this. So you can say benzoic acid react with sodium hydroxide. Now for us to calculate the milli equivalent, this is one thing that you must take note of. Are you getting it now? Now let's calculate the molecular mass of benzoic acid. I can just say molecular mass of benzoic acid because of time. Molecular mass, I think it's 122, but everybody knows how to calculate for molecular mass now by adding all the atomic masses together. All right, molecular mass from benzoic acid is 122. That means when I mean adding all the atomic mass, carbon is 12 times 7 plus hydrogen 6 plus this one 16 times 2 will give us 122. So you can come here and say 122 gram of C7H6O2 will react with how many moles of sodium hydroxide? Will react with 1 mole of sodium hydroxide. So you can come here, this will react with 1 mole of sodium hydroxide. Now this is where some persons actually have issues understanding this 1 mole of sodium hydroxide. From the equation of reaction, if you look at it very well, this is also 1 mole. React with 1 mole. But now we want to get the gram equivalent that will react with 1 mole of sodium hydroxide, because sodium hydroxide was given to us in what? In concentration. If you look at it, the practical, they gave you that the amount of sodium hydroxide that reacted is 0.5 mole. That she reacted with 0.5 mole. So we must get the milli equivalent of 0.5 mole. Is that okay? But you know that 1 mole of sodium hydroxide, number of moles is what? You just come and do that little calculation at this corner here. What is number of moles? Number of moles, or firstly, what is molarity? From what you learned, that molarity is equals to number of moles over volume. So our number of moles will be molarity times volume. Now, what is the number of moles here? Number of moles is 1 mole. Are you getting it now? It's different from the molarity. Molarity is a concentration, which is this 0.5. That is what we are trying to get. Now, molarity is, number of moles is 1 mole. So we are going to do it in such a way that the number of moles must be 1 mole. That means our molarity times volume must be 1 mole. And the only way that can happen is when our molarity is 1 mole times our volume is 1 liter. Because molarity is usually measured in liter. So 1 mole times 1 liter will definitely give us the number of moles to be 1. Are you getting it? Let me do that again. Number of moles is what? Molarity is what? Number of moles over volume. Our number of moles will be what? Molarity times volume. But our number of moles here is how many? 1. So we want to do the manipulation, not manipulation, sha. You want to do it in such a way that when you multiply molarity times volume, it must give us the number of moles as what? 1. And the only way is when the molarity is 1 and the volume is also 1, but it must be in liter, because molarity is usually graded in liter. So we can say 1 mole times 1 liter. Now we want to look for the milli equivalent. That means the milli equivalent, you must always use milliliter. So this becomes 1 mole times 1 liter is what? 1000 milliliter. So in place of the 1 mole, which is the number of moles, you are now going to substitute 1 mole times 1000 liter. Are you milliliter? So this gives us 122 gram of C7H6O2 would be equal to 1 molar solution, then 1000 milliliter of sodium hydroxide. So this have replaced this 1 mole here. Now milli equivalent means how the mass of benzoic acid that react with 1 mole of 0.5 mole, because the concentration they give to us here is what? 0.5 mole. So by standard, that's what we are trying to find. By standard, what mass of benzoic acid will react with 1 milliliter of 0.5 mole 0.5 molar sodium hydroxide by standard. So you are now going to come here and say, one way to do that is, firstly, convert this 1 molar solution to 0.5 molar. Now, the thing is that anything you divide here, you must divide here. But you cannot divide these two at once. It's either you divide 1 here, divide 1 here. So we want to convert this 1 molar, because what was given to you was 0.5 molar. If here we are to be, let's say, 0.1 molar, you divide by a value that will convert this one to 0.1. But since it was given 0.5 molar sodium hydroxide, that was the concentration of sodium hydroxide that reacted. So you convert this to that by dividing by 2. If you divide here by 2, you also divide here by 2. This will give us what? This will give us 61 gram of C7H6O2 is going to give us 0.5 molar 1000 ml of sodium hydroxide. All right. Now, having done that, the next thing you now need to do is, but we are looking for the milli equivalent. That means what mass of benzoic acid will react with 0.5 molar 1 ml sodium hydroxide. Now you are going to know why we are looking for this, because I know over the years we've been solving this practical, but we don't really know what we were doing. So when this cancel this is going to give us, this divide 61 divided by 1000 is going to give us 61 divided by 1000. 122 divided by 2, 61 divided by 1000. That is 0.061 gram of benzoic acid. All right. Now, I believe you understand how I did it to this point. 0.5 molar sodium hydroxide. But if you see the question, what was given was 0.2 molar sodium hydroxide. So you must be very careful of what was given in the main question. 0.2 molar sodium hydroxide. So if you look at it here. What I mean is titrate with what? 0.2 molar sodium hydroxide. Are you getting it now? So what we are going to do is to make sure we convert this 1 mole to what? 0.2. And the only way to do that is by dividing this 1 mole by what? By 5. Because if you divide 1 divided by 5, it's going to give us 0.2. Now, according to what we have done before, this 122 will also be divided by 5, because I say anything you divide here, you divide here. So it gives us 122 divided by 5. 122 divided by 5. That will give us 24.4 gram of this will react with 0.2 mole of 1000 milliliter. Now, listen, the next step is we want to convert to the milli equivalent. Now, to convert to the milli equivalent, we divide by 1000. So we've already divided here by 1000. Come here. You divide here by 1000. All right. And when you divide by 1000, this is going to give us 0.0244 gram of C7H6O2 to give us 0.2 molar 1 ml sodium hydroxide. So this is the milli equivalent. Now, the molecular interpretation of this, let me say the interpretation of this, the common sense idea of this one is, it means for every 1 milliliter of 0.2 molar sodium hydroxide, this is the mass of benzoic acid that react. You know this thing, this sheet here is benzoic acid. Are you getting it now? It's just a common sense idea. For every 1 milliliter of sodium hydroxide, are you getting it? This is of this 0.2 molar sodium hydroxide, which was what was given. This was the amount that react. So if you have 1 ml of sodium hydroxide, this is the amount that will react. How about if I now have 10 ml of sodium hydroxide, which understanding now, you can just say 1 ml, 0.0244 gram of benzoic acid react with what? 1 ml sodium hydroxide by standard. Therefore, you are now going to come here. If let's say your theta value is 10 ml for sodium hydroxide, let's say sodium hydroxide theta value is 10 ml. You now say 10 ml will react with what? X. From here, cross multiply. So X will be 0.0244 gram times 10 ml of sodium hydroxide. Are you getting it now? But I mean times 10 ml of benzoic acid that reacted. But all these ones, you don't need to just bother yourself about this relationship. All what you need to do here is what I'm going to show to you. So having ascertained your theta value, because when you have gotten this is now what we call the milli equivalent. This old sheet here is what we call the milli equivalent. All right, the milli equivalent. Now you are now going to come back. This is the general idea of this practical. Now let's say you have something like this. I said this is hypothetical table of values for the titration. That means hypothetical. After you titrate, this is what you got. Now at the end of the day, let's say this is for the organic phase. The first one is for the organic phase. Volume of base used, that means volume of sodium hydroxide used, is 10.20 and 10.10. So you are going to say 10.20 plus 10.10. The average volume will be 10.20 plus 10.10 divided by 2. 10.20 plus 10.10 divided by 2, which is 10.15. So for the organic phase, the amount used is 10.15. While for the aqueous phase, the amount of base used, is this still the same? No, it can't be the same. Oh. This is an error. It can't be the same. So these are your theta value for the aqueous phase. Now what will be the average value used? Now recall that this is calibrated in centimeter cube. Centimeter cube is still the same thing as milliliter. Still the same as milliliter. So this is going to give our average volume used here will be 1.10 divided by 2, which is the same thing as 1.10 centimeter cube, which also approximates to what? 1.10 milliliter. So for the first one is 10.15, while for the second one is 1.10, because I know if I get out from this space now, this whole thing will delete. So 10.15 and 1.10, 10.15 and 1.10. So I can come here, right? 10.15 and 1.10. This is for organic phase and this is for aqueous phase. All right. Now there was something that we did in the practical that I'm not too comfortable with chemistry wise, but since all of us dubbed, the dubbing went well. But however, that is not the proper thing for us to do. All right. Now we have organic and then we have the aqueous phase. The next thing we need to do is to calculate the concentration in the organic phase. That means the amount in the organic phase. And to calculate the concentration in the organic phase, you don't divide by the theta value. You multiply by it. Are you getting it now? So concentration in organic, so we can say concentration of benzoic acid, let's use A, in organic phase would be equal to, in the practical we divided, but I'm not too comfortable with it. Because if you say this is equals to this, we are not supposed to divide, rather we will multiply to get the amount in 10.15 ml of sodium hydroxide. Recall that these values you got here are the amount of sodium hydroxide. So the interpretation is very easy. If 0.0244 gram normally by standard, by the mole ratio or by the equation, is reacting with 1 ml, it means 10 ml of the sodium hydroxide will react with how many grams of benzoic acid? Because we want to know the amount of benzoic acid present, right? That is what we are supposed to do. So if 0.2 react with 1 ml, 10.15 ml, centimeter cube is still same as ml, supposed to react with what? X. So when you cross multiply, at the end of the day, supposed to give us multiplication. So this is supposed to give us the concentration in the organic phase will be 0.0244 gram times we have 10.15 ml times the factor. The factor is 1. Are you getting it? But you don't need to put those ones because that is not what you are interested in. Now when you multiply these two things, it's going to give us 0.0244 times 10.15, which is going to give us 0.24766. Now that in the aqueous phase will still be this milli equivalent, because you want to know the amount in the aqueous phase and the organic phase. You still use sodium hydroxide. So it means if 0.0244 gram react with 1 ml in sodium hydroxide, then 1.1 ml will be equals to X2 when you cross multiply. This will give us this is supposed to be gram ml. Are you getting it now? Gram, not gram per ml, gram multiplied by ml, because this thing is supposed to be gram per, this is one concentration term. So this is supposed to be 0.0, then we have 244 gram times 1.10 ml, which equals to 0. Let's multiply 0.0244 times 1.10, with 0.0268 gram ml. So this is the concentration in the organic phase and in the aqueous phase. Now we said that for partition coefficient, an equilibrium exists between the organic phase and the aqueous phase, and that gives us the general idea of partition coefficient or partitioning. What we mean is that in partition coefficient we have something like this. There's an equilibrium that exists in such a way that you have the concentration in aqueous phase is in dynamic equilibrium with the concentration in organic phase. So when you find the constant, the equilibrium constant, which is also called the partition coefficient, it will now give us the concentration in the organic phase divided by the concentration in the aqueous phase. And that is the definition of what? Of partition coefficient or distribution coefficient. We say the partition coefficient or distribution coefficient is regarded as the ratio of the equilibrium concentration of the organic phase to that of the aqueous phase when a particular substance is actually partitioned between two phases. That is what the partition coefficient is all about, or the distribution coefficient. So in this case now, haven't defined, because one of the questions here say define partition coefficient. You've defined it, or what is partition coefficient? Now, this question, just one thing could have changed this question to what is the partition coefficient? Are you getting it now? And I believe that is what they are asking for. What is the partition coefficient, or what is partition coefficient? Now you've defined, if they say if the definition is what they want, you've defined it. Then what is the partition coefficient? For this question, you have to actually solve for it. This is now going to give us KPC is equals to the amount in the organic phase is what? 0.24766 gram mole divided by 0.02684 gram mole. When this cancel this, these two multiply each other, what is it going to give to us? It's going to give us 0.24766 divided by 0.02684, and this will give us 9.22. So that is our partition coefficient. Is that okay? That is the partition coefficient for this particular one here. All right, are you getting it now? So that is generally the differences, the partition coefficients in this particular question. It's kind of very easy, right? Now, sometimes some of you may be wondering, why do we have to undergo all these procedure where this thing is something that we've been taught in secondary school? C1 V1 is equals to C2, C1 V1 all over CB VB is equals to NA all over NB. Now let me try and use that one to solve and see if we get the answer too. We have CA VA, you can still remember CA VA all over CB VB is equals to NA over NB. True or false? True. Now in this question, what is your CA? The concentration of the acid is unknown because that is now what you are going to look for. Now, but you know that this concentration will be in mole per dm cube. It will be different from what we got here, the concentration we got here. Concentration will be in mole per dm cube. Now, what about the volume? VA would be the volume of the acid that they say you should pipette was 10 ml, because they say you should pipette 10 ml of the different phases, and the acid is what is contained in those phases, because they say benzoic acid was actually partition. Are you getting it now? So the volume of acid will be 10 ml. Benzoic acid is what is there. The concentration of the base is 0.5 molar, and then the volume of the base was the volume, the title volume you got. The title volume was 10.15 for organic phase, and then what? 1.10 for aqueous phase. Now, the Na is what? 1. The number of moles of acid. Then we also have number of moles of base. Nb is also 1. So substituting, we can come here and say organic phase. Let's start with the organic phase. Now for the organic phase, Ca is what we are looking for. Va is 10. Let's just write 10 ml. Divided by Cb is 0. Why am I always writing 0.5? 0.5 don't to just in my head. The concentration of the base given was 0.2 mole, not 0.5, please. 0.2 mole times volume of base is 10.15. Are you getting it? Because that is the title value. The volume of base that you use, the volume of the sodium hydroxide that you used, all right, is equals to Na is what? 1 divided by Nb is 1. So this becomes 10 Ca is 0.2 times 10.15. So divide both sides by 10, and then your Ca, this cancel this, will be equals to 0.2 times 10.15 divided by 10. That will give us 0.203 mole per dm cube. So the concentration of the acid, which is benzoic acid, for the aqueous phase, for the organic phase, concentration in the organic phase, which is organic, concentration of A in organic phase is what? 0.203 mole per dm cube. Now this one is mole per dm cube. What did we do in our previous one? Now is gram per mil, gram mil. Are you getting it now? Exactly. It's different. The units are different. But at the end of the day, your partition coefficient will give you the same thing. So I'm just telling you that everything we do here is the same thing with what you did in your secondary school. But then the whole thing is seeming difficult with this idea of milli equivalent. But the milli equivalent is more easy if you understand the process for it. Now, the next one is that for the aqueous phase. So for aqueous phase, CAVA will still remain. CA is what? Unknown. VA for aqueous phase is, VA is 10 mil, still 10 mil. Divided by CB, concentration of base 0.2, times VB for aqueous phase, the volume of base used is 1.10. NA is 1, NB is 1. So this gives us 10 Ca is equals to 0.2 times 1.10. Divide both sides by 10. This is going to give us Ca is equal to 0.2 times 1.10. This is 0.22 divided by 10, which is going to give us 0.022. Now, what is the unit for this one? Still mole per dm cube. Are you getting it? Mole per dm cube. So the concentration, concentration have different units now. In the aqueous phase is 0.022 in mole per dm cube. Now, coming here to find the partition coefficient. What did you say is the partition coefficient? We say partition coefficient is Kpc is what? Concentration in organic phase all over concentration in aqueous phase. Are you getting it now? And then at the end of the day, values now become, in organic phase is 0.203 mole per dm cube. Partition coefficient does not have any unit because it's going to cancel out. This is 0.0222 mole per dm cube. This will cancel this, and then Kpc would be equal to, we have 0.203 divided by 0.022. What did it give to you? 9.227. Now, is it not the same thing with what we had earlier, the partition coefficient? Go and check. If you scroll up, you see that the partition coefficient we had earlier was what? 9.22. What do we have here too? 9.22. So you see that everything is the same thing with everything we'll be doing in secondary school. CAVA equals to CBVB. But this idea of milli equivalent is just more shorter. Are you getting it now? So that is the reason why I told you guys that calculation we did, because what we did in the practical was we divided like this 0.0244 gram. We now divided it with the amount of sodium hydroxide that reacted. It ought not to be so. Are you getting it now? I believe with this you've been able to cover everything up there. Now the next thing we ought to understand now, okay, the next thing they say we should do is state the precaution. Now for this experiment, the precautions are straightforward. What are the precautions? Now when you are separating both layers, you make sure that one of the layer, when you are actually separating the two layers, like you want to separate them, you ensure that one layer does not get to enter into the other layer in your conical flask or whatever flask you are using. What I mean is that, look at it. Let me come back here. That is one of the precautions you took during the experiment. These are the two layers. You make sure that this yellow part, come enter this part here. Are you getting it? That is one. And you make sure that another precaution is that you make sure that the endpoint is accurately taken by the first color change. That means you should not wait until very, 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 very thick before you now start taking your endpoint. That first color change that is persistent, which is pink, that is where your endpoint should take. And you should make sure that you actually mix it very, very well. Are you getting mix the content of the separating funnel very well by shaking vigorously to ensure that they mix very well before the separation take place. So these are some of the general precaution. Of course, general precaution in the lab that you took to ensure that you have stability, a good practical. Now, the next thing you will ask is write the structural formula of benzoic acid. I've already drawn that one. What is structural formula of benzoic acid? Formula of benzoic acid. Because most times when you are reacting it, you will not draw this one. Some persons will just write this equals to 1 mole of this. That's usually why they say you should draw the structural formula of benzoic acid. This is benzoic acid. Is that okay? So you can come down here and actually state that structural formula for benzoic acid is this. So with this now, what you are going to do for me is take your own values, impute them into what we just did now, and see if we are going to have the same answer. And also do something for me. You know, the one we did in the practical was we divided. When I mean we divided, this benzoic acid, I'm going to show you, I'm coming. So we know that we answered all the question. Now what I mean is, no cancel. Come up here. These values you got here, because when they say calculate the quantity, the concentration, what most of us did in the practicals was, for that of organic, we divided, like it became 0.0244 divided by 10.15. You will get a value. Now, if I want to even do that here, let me just do it once and for all, so that you see that it will not give us the correct answer. 0.0244 divided by 10.15. That will give us 0.002403. And then the next one is 0.0244 divided by 1.10. This one I give us 0.022. Right? You say gram per mole. And this is gram per mole. Now, with even this thing you have given here, what you are trying to tell us is that for 1 mole of this is the amount in gram that is present in the organic phase, which is a lie, because the amount in mole that is present in the organic phase supposed to be much more than the amount in gram rather that is present in the aqueous phase, since benzoic acid is an organic compound. It's supposed to be more soluble in the organic phase than the aqueous phase. So that calculation we did there is a very wrong calculation. I don't know who invented it, but you know it's always dubbing and dubbing, so we continue dubbing. But this is the right thing for us to do. Now, any partition coefficient question that will be given to you, this is the right approach for you to go. You can use C1 V1 if that one is the one that you actually understand. You still get the same answer. All right. Thank you very much for your time. We are going to see in the next one. Bye.